Good morning. Okay, today we're going to talk about this mechatronic systems. As you can see on the screen here, this is a sensor and it's a piezoelectric sensor model. It's called a mechatronic systems, huh? Mm. Okay, here's the objective. We have a mechanical input in here, and we are going to look at an electrical output over here. So let's just switch color pens in here to make these notes. And in here, this is your input in here. And this is our output over here. Okay, so let me just will make myself disappear for now, and I will continue on with our notes over here. So there you go, electronic system. So this is my input and this is the output over here. So we need to establish a transfer function between this output and this input to do this lapping here. But what is important here is to understand the concept of the transfer function. So why don't we just define it in here? You could say transfer function. What is this? This is a relationship between the output and the input. So this is the output over the input. So in terms of the if we write it in the domain, in this case you could say the voltage across the capacitor divided by the input U in here. This is your transfer function. Maybe we could call it T-fun for transfer function. If this is true, doesn't it follow that the output is equal to T-fun times the input? Let's just write down exactly what the input was, and that is this input U. So what it's saying is, if we could just maybe write it down here, it says the output is equal to the transfer function times the input. All right. So if this is the case, it follows that if we know the transfer function, as we do here, if we know this ratio, we could perfectly well obtain an output giving a certain input. Right? Does that make sense? Okay. So what we are going to do in this case is we are going to give an output here at a certain frequency and find out what the output is over here. Then we're going to change the frequency input in here and then see what the output is over here. So we are going to look for the input is going to be of this kind, like this. Yeah, this would be the input here. So it's just a sinusoidal input like that. But the output, as we received it over here, this output might be a little bit out of phase, not necessarily exactly in phase with the input. Okay, so this is the input frequency, and this would be the output frequency. So in this case, we have, like I said, the output is B sub c here, and the input is u. And this is the acceleration in this case. Here it says u double dot is the input. So this, in order to, you may say, quantify this, we have set up special plot in which we are going to look at plotting the response of the system, the output of the system, and we are going to go on the horizontal scale. We're going to put the frequency. Yeah, and in here we're going to put the output, which would be B sub c. So in here, what is going to happen is we'll start with something like this, and maybe it will taper off like this, and then it will do something like that. And this is going to be around, let's say, 1 hertz. Then it will be 100 hertz, 1000 hertz, logarithmic scale. This point in this particular sensor, you might be about 10 to the 4th. But what we are doing is we are giving a frequency input in here, and magnitude, of course, of the oscillation, and obtaining an output over here, and we are plotting it here. So this is what we call the magnitude in this case. But companion to this, if we plot how much in phase or how much out of phase the input is from the output, frequency. And the difference between these two is, it would be the so-called phase angle. See, phi, so this is the phase. And this might do something like this. So, but again, we have a 10 to the 1, 10 square, like this. This set of both of these plots is called a body plot. Okay? So it is important in this case to find out whether the input and the output are all in phase, and whether the input and the output are also the same. So if they are the same, the input and the output, the magnitudes, then it's going to remain constant, and this is going to be a ratio of 1, right? So that's what we're interested. We're interested in this region, whether when the ratio of 1 is achieved. So the sensor is good from this frequency to this frequency. And before this and before that, the sensor does not measure exactly the same input being, the output be the same as the input. So just to clarify this, if I can make the plot of the input and the output together, it would look something like this. See, and the input would be like this. And then we will plot the output. Let's change color. If we plot it on the same, let's just, you see what I mean? I have managed to create one that is exactly 90 degrees out of phase. So the difference between these two would be the difference in the angle. So the input is 90 degrees out of phase with the output, or say the other way around. The output is 90 degrees out of phase with the input. So those are the kind of tests that we need to do for this analysis of the sensor. So a little bit more on how it works. We can look at it this way. You have a mechanical input in here, which is the acceleration, and this is a mass in here. If you have an input in here and you have this piezoelectric material, if you get an input from the housing, the mass is going to try to stay in place and compress this material. This is the piezoelectric material right here. What it means is that when that happens, it produces a small voltage, and of course is connected to the housing through this spring and the damper over there. But it's very obvious that if I give an input in here, because of the property of this material, that is the piezoelectric, it will produce a voltage here. But in order to measure this voltage, I need this amplifying circuit. Now, the way this works is this device in here is called an operational amplifier. It has external power so that it can actually amplify the signal that comes in here to what you get out here. In order to achieve this, it's set in such a way that the current here is 0, but the voltage is not. And in order to do this, do you see what happens here? The current over here has to be equal and opposite to the one over here, because this minus this should be 0, because this is 0 also. Okay? So if you have the voltage is not 0 here, the voltage multiplied by this amplifying constant is equal to the output over here. So this circuit would allow us to measure the signal that was produced over here and be able to see it. So here's your mechanical side. And this is your piezoelectric transformation. You see when we put it, piezoelectric transformation. And then you have here is your electrical output. So that's how we are to do this lab. So what we need to do in this case is to put together the